Okay, so in this question we have a predominantly rolling without slipping problem. Part E will talk a little bit about some differences between rolling with and without slipping, so it's still kind of important to remember sort of those differences. So part A, we're trying to figure out how fast this thing is moving at the bottom of the inclined plane. And there's kind of an easy way and a hard way to do it. The easy way that I'm going to do is conservation of energy. The hard way involves sort of solving part C first to get the acceleration, then using the acceleration and the distance to get the speed. But since you have to do the acceleration in part C anyway, it's kind of the 6 of one, half a dozen of the other in terms of the total amount of work. But I'm going to do the energy conservation way first. If, as you approach this problem, you couldn't figure out how to do it A, but you got part C and then use C to get A, you'd still get the points. Like that is physically correct. So, part A. How fast is it moving at the bottom of the inclined plane? Well, energy is conserved, right? There are no non-conservative forces acting because the friction force is a static friction and not a kinetic friction, so we don't lose any energy. So, we start off with only gravitational potential energy, and we end up with both types of kinetic. So this is mg, and I'm going to use capital H like they do. The translational energy, 1/2 mv squared. The rotation, 1/2 I omega squared. And now we just need to start simplifying and cleaning things up. So mgh is fine. 1/2 mv squared is fine. So the moment of inertia, we are given the moment of inertia of the disk, and we want the speed v, translational speed, so I'm going to replace omega with v over r, and then squared. So that will cancel the r's. We see there's an m in every term, so we cancel those. And now we can combine some stuff. So gh equals 1/2 v squared plus 1/4 v squared. Gh is 3 v squared over 4. V squared is 4gh over 3. Or, our final answer, v is the square root of 4gh over 3. You can take the 4 out of the square root if you want. That's fine, but this is sufficient as an answer. Okay? So that's part A. That's how fast it's moving at the bottom of the inclined plane. So part B, we need to do a free body diagram. So we have our sort of side view of the cylinder. And since this involves rotation, we have to draw all the forces sort of where they're applied. Right, so I'm going to draw in as well sort of the incline that it's sitting on, just kind of as a reference. So that's kind of the incline it's sitting on right there. Okay? So we have a couple forces. First, friction. That's why it rolls. You have to have friction. The problem does not say anything about it, but it cannot roll without slipping if you don't have friction. So you have to have friction. Right, so it points up the incline, force of friction. We have a normal force, which is also at that point of contact. And then finally we have a weight. Oops, I drew that stupidly. We have a weight. Right, so those are the three forces drawn at their points of contact. Okay? And it's very important to get all the directions, labels, and point of application. Right? You have to get all of that to get the points. Okay, so in part C, we could go through Newton's laws, but we already kind of know a bit more about the situation because of this piece right there. So we know our initial and final velocities and the distance we travel and what the acceleration. So we can use a kinematics equation for that and save us some time. Again, as I was saying earlier, you can do part C with Newton's laws from scratch and then use the acceleration to figure out the speed. But that is really more work with the kinematics way. So we know we have a constant acceleration. So v final squared is v initial squared plus 2a delta x. So let's start substituting things in. So v final squared, 4gh over 3. The initial squared, 0. A is what we were trying to find. So delta x, right, is the total length we travel, not like a component or anything. So if this is h, and that's theta, then we want, I guess I'll call it delta x. We want that part of the triangle. That's a sine relationship, right? Sine theta is h over delta x, or delta x is h over sine theta, right? So plug that in, h over sine theta. Okay. And now we can solve. We can see that since that initial velocity is 0, there's an h in both terms, so we can cancel that. We have to multiply by a. Actually, before we do that, we can cancel the 4 down to a 2. We have to multiply by sine theta to get a by itself. And so we get 2g sine theta over 3 equals a. Right? Much easier than Newton's laws. If you wanted to do Newton's laws, you would need to solve this series of equations. So I'm not going to do because it'll take a long time and I'm lazy, but I'll set them up, right? So F equals ma and tau equals I alpha. You'll need to solve that system. Well, the net force, and this one will be the down the incline path. So you'll have mg sine theta, which is the weight of gravity pulling down the incline, minus the force of friction, equals ma. And the net torque is only due to friction. So friction times r equals 1/2 mr squared, and then a over r. So as you can see, we have, in both equations, we have two unknowns, right? Everything else we know. And so we can combine those to eliminate f and solve for a. That would be the long way, but it does work. So if you think Newton's laws first and you're comfortable with that, do it that way. It works. Okay, so that's part A, B, and C. So part D, we need to figure out the minimum amount of friction that is required for the cylinder to roll without slipping. And for this, there's really kind of a couple different approaches. So I'm going to use the one, assuming we know the acceleration that we have. We can use F equals ma to find the force of friction that's sort of like left over. So that's if I go back to this approach, we found A, so now we're going to use this equation to find F. So we'll kind of go with that approach. So ma is mg sine theta minus F. And we know everything except for the force of friction. We need to rewrite that. So ma is mg sine theta minus mu times n. Now the normal force, right, is not just the weight here because we're on an incline. It only balances the sort of the perpendicular to the ramp component of gravity. So it's not just mg, it's mg cosine theta, a little bit smaller. So we notice we can cancel a mass out of all of these. And now we're going to plug in A, which is 2/3 g sine theta. So we can cancel all the g's. So we get 2/3 sine, well, we get sine theta minus 2/3 sine theta. So we get mu cosine theta equals 1/3 sine theta, or mu equals 1/3 tangent of theta, right? If you have that coefficient of friction, then you get the proper acceleration to make it roll without slipping, right? There is another way. Actually, there's a couple other ways, but the other one I think is kind of neat is that the rolling without slipping condition in terms of accelerations is that alpha r equals a. And so we know what a is, right? We just found that. That's the g g sine theta 2/3. And so we can get alpha as well in terms of the friction force. Right, this can come from tau equals I alpha, where tau is going to be the force of friction times the radius. So that's mu k mg cosine theta r equals 1/2 mr squared alpha. So you can solve that for alpha. You plug that in. Actually, I should make this a capital R. And so we have, right, we have one unknown mu k. You can solve that and you get the same answer. That's another way you can do it. You still kind of need Newton's law, so it doesn't really change anything, but it's another option. So if we have this coefficient of friction mu or anything bigger, then it rolls without slip. So part E has a couple different parts to it, and they're explanation, not calculation parts. So we'll probably do a little bit of math. So we make the coefficient of friction less. And so we want to know, now that it's rolling and slipping, what happens to the speed? Well, if it's rolling and slipping, that means it gains less rotational energy. It's doing less rotations for an amount of distance traveled. So if it has less rotational energy, but energy is still conserved, right, we still have only energy mgh available, then this is now going into less k rotation, so it must go into more k translation. And so therefore v must be larger. Okay. Now, there is kind of a caveat to this, which is what we're going to see in part 2, is that yes, we have the total energy available, but if it rolls with slipping, we've introduced a new type of energy, and that's heat, or the thermal energy concept, because when it slips, friction is now a non-conservative force doing work. When it didn't slip, the friction force never did any work, so we didn't lose any energy to it. So even though the speed is larger, right, because we have sort of a bigger percentage in translation, the kinetic energy is actually less, because we're converting mgh into k, both types, plus delta E thermal now. And so this must be less than before, right? So, so even though we convert a greater percentage of the total into translational kinetic energy, so the speed goes up, we convert some of it as well into thermal energy, so we have slightly less total kinetic energy than before. And the key is that, right, this is friction, right? Friction does work in some sense.